All right, so hello everybody again. In this video, I'm going to just finish up what we're discussing about privacy preserving, and then just finish up with trustworthy AI, so that we can start a new concept in the next lecture on Wednesday. So far we talked about privacy preserving machine learning. Give me a second, all right. Sorry about that. So we talked about homomorphic encryption. We talked about fully homomorphic encryption and somewhat homomorphic encryption, right? We talked about the basics of homomorphic encryption, how it works, and why it's secure, and so on and so forth. So now let's talk about the other methods for privacy preserving. If you remember, I gave you a long list of other things that we can do. And the first thing that we want to discuss is the multi-party computation. We already kind of a little bit talked about it, and I gave you this problem of millionaires problem. I told you that this is actually one of the oldest problems in this domain. And we also kind of intuitively talked about what are the solutions for it and how we can fix this problem, right? So now let's actually talk a little bit more systematic and see for any given problem how we can solve this. I also gave you this example for finding individual numbers and finding the sum of the individual numbers. And I said that essentially what we should do is assuming that there is like one malicious player and n players, and only one of them is malicious. What we can do, we can have this systems of sending information to the next person and next person, adding some noise to it, and assuming that there's only one person that is malicious, it is guaranteed that the system can work properly well. Assuming that this person can, just reduce and cancel out this noise, and then again just send out the sum to everybody else using this round robin kind of, method. All right. So what is very important in multi-party computation is the assumptions about the systems. How many people are we assuming that are malicious? Is it more than half, or less than half, or is it one, or is it multiple, so on and so forth? Because, for example, in the solution that I gave you, even two malicious users can potentially break down the system. So assumptions really matters in multi-party computations. Slightly different than, for example, homomorphic encryption, where essentially the assumption there is the system is secure if the encryption system is secure. But here it's slightly more than that. So different algorithms can be secure or not secure depending on the assumptions that we have. And as I said, there is this interesting concept called honest but curious. So essentially in MPC systems, we typically have this assumption. So we are basically saying that all the players in the game follow the rules and protocols in the game, but of course they are curious to understand what is the value of the other users in the system. But they're following the protocol. So for example, if they have to get a value added to their own value and send it to the next person, they will do that and they follow that protocol, right? So let's now talk about the more generic solutions for multi-party computation. And there are multiple solutions for it. Yao Garble circuits is the most famous one. GMW is another protocol. There are other different protocols as well that exist in the system. So we want to mainly talk about the Garble circuits, or GC, right? And the protocol that I'm going to show you is mainly for two parties, but we can actually extend it to multiple parties. I'm going to talk about that a little bit later as well. So the main observation in garbled circuit, the first steps in getting garbled circuits initialized is that essentially we show any function as a combination of gates, right? This very same idea that we built, RTL systems and digital logics, essentially GC also kind of like do the same thing. So given any function, what we first do is we create the gate level equivalence of the problem and the solution, and then we basically create the gates for the system, all right? How do we do that? There are standard methods for it. Probably you can go back in and look at your digital logic course if you have ever taken it and see how we can do that. But for now, this is not important. Let's see that, that the problem is actually reduced to some circuits, all right? So what we get is like, list of gates and inputs and outputs connected to each other, and then maybe some, NOTs and maybe some XORs and so on and so forth, coming from, let's say, one of these inputs. And then it's continuous, right? So it could be a complex gate and so on. So what we need now is basically showing that how any two input gates can be evaluated. And once I show you how that part can be done, the rest is just, repeating this process for this gate, for this gate, for this gate, for this gate, and so on and so forth, right? So as long as I show you that we can do it for any given gate with two inputs, then you essentially just repeat this process for every gate, and then you go start from the beginning all the way to the end, and then you get the results, right? So this is the way that GC will work. And the example that we're going to give you is for the AND gate, but it doesn't matter. It could be for any other two input gates, all right? So the assumptions that we have is that we have two players, Gini and even. We're going to show them by G and E. And since this is a multi-party computation, obviously one of them has inputs for one of the inputs. So let's say this is the AND gate that we have. So one of them has this input and the other one has the other inputs. Of course, if one of them has both inputs, then the multi-party computation wouldn't be needed, right? So they can just basically locally compute the AND value and move forward, right? So the idea here is that, the input is partially shared between them. And what is interesting for us and for both of these two players, Gini and Even, is this out, right? And then here, what I'm showing is the truth table of this gate. So this is nothing but, basic digital logic design. So we show it by G and E, and the output is the AND of these. 0, 0 would be 0, 0, 1 would be 0, 1, 0 also 0, and then 1, 1 is 1. This is just a classic truth table for AND, right? So nothing new so far. So now let's continue. So the very first step after actually initializing the system with the inputs in truth table is what is called garbling, all right? And for the garbling, one of these two players has to be the garbler. All right, so either Even or Gini, doesn't matter which one, just one of them has to accept to be the role of the garbler, and the other one becomes evaluator. All right, so now let's, for example, assume that Gini is the one who is garbling the circuit. All right, so what is the process of the garbling? The process of garbling is basically two things. One is for different inputs, for G0, G1, E0, and E1. We have these four different inputs, right? Either G is equal to 0 or G equals to 1, E equal to 0 or E equal to 1. To just remind you what G and E are basically these two things. We call this G, we call this E. So either this one can be 0 or 1, or either this one can be 0 or 4 different options, right? As we've shown here. So what we do is that we create random labels for these inputs. So we don't say G0 or G1. Well, what we do is say that this is basically a random input. So let's say, for example, for any 10 bits, 1 or 0, 0, 1, we create an 8 bits random number, right? So just something like 0, 0, 0, 1, 1, 1, 0, 1. Just a random inputs generated from some random distribution. All right. So what the garbler will do is create 4 of these inputs. Let's say each of them L bit long. All right, L bit, which L in this case, for example, is equal to 8. All right. So we're going to talk about. There is some rationale behind like how long the length of each bit should be, but for now, just imagine that it's typically much larger in order of like 8 bits or 16 bits or 32 bits long. So we are substituting the zeros and ones with some labels, and we call it W. All right. So that's the first steps. Then the next steps is basically encrypting the outputs. So what we do is that kind of like also assigning some labels to the outputs. But in order to make the inputs as a function of make the output as a function of inputs, what we do is we create some encryption. Let's say something like an AES, which we're going to talk about in the next lecture. So let's say there's an encryption mechanism such as AES. So what we do is that we create an encryption for input 0, for the output 0. And for this input here. So as you can see, the input is labeled 0 for G and labeled 0 for E, right? So because 0, 0 is the inputs for this specific one. And this H function is basically some sort of hash function in order to make sure that based off these 2 inputs, we create some hash. Once we talk about the encryption mechanism, we'll talk about why we need something like a hash. But just imagine that what we do here is basically an encryption mechanism that has kind of 2 keys, this key and this key. So in order to decrypt this, anybody who wants to decrypt this has to have this value and this value. If it has both of these values, then they can decrypt it. So think about it as a box with 2 locks, right? Which one of them is W0G and the other one is W0E, all right? So if anybody has these 2, they can actually unlock this box, which is the decryption, right? So the second step, as I said, would be the encryption. So the attacker first creates these labels, and then using these labels, will create an encryption mechanism, an encryption value for each of these lines here. All right. So at the end of this process, what we will get is just 4 values. So think about it as just a random looking zeros, 1, 1, 0, 1, 0, 1, 0. Let's say, again, just to make things simple, let's say these are 8 bits values, all right? So what this encryption does is basically it gets 2 8 bits values with some algorithm for the encryption. It'll create an encryption, so send out another random looking values. And these are the outputs of this table. Then there is another process which, in order to kind of like, decorrelate these values for each row, and just by looking at it, you cannot tell which row is which. There is a random permutation steps as well. So what it does, basically, the garbler is just moving these things around in arbitrary direction. All right. So as you can see, for example, this is 0, 1 inputs, this is 1, 1 inputs, this is 0, 0 inputs, and this is 1, 0 inputs, right? So originally we had 0, 0, 0, 1, 1, 0, 1, 1. Now with this random permutation, we have 0, 1, 1, 1, 0, 0, and 1, 0. All right, so we just move around these things. We move this to here, we move this to here, and so on. The reason for that is that when we are sending these 4 values to the evaluator, it doesn't show that the first one is actually 400 or the second one is 401. So it's just completely random. All right. So that was looking at this, boxes or this encrypted values, they cannot tell which one is which. Right. So that's the idea of this random permutation. Right. So now this is the last part for the garbler, which we in this specific example, we assume that Ginny is the garbler. So she creates the random labels. She encrypts the output using this random labels, and she creates a random permutation of this encryptions. So then she's going to send this table, this permutated label table here. So she's going to send this one. She's going to send this one to she's going to send this one to even, right? So basically 4 values she's going to send. Another thing that she's going to send is her input, all right? So her input, so if her input, so Jeannie's input is equal to 0, she's going to send W 0 and G. If her input is equal to 1, she's going to send W 1 and G. And remember, she's not sending 0 or 1, she's sending these random looking labels, right? So what even will see is just an random looking 8-bit value, and he has no idea whether this is equal to 0 or is it equal to 1, right? So this is just a random looking label. So let's say, for example, if I have zeros and ones, instead of sending these values, I give you a name of an animal. So like I send you monkey or cat or dog, right? So by seeing monkey or cat, I cannot understand whether it was 0 and 1. And the important thing is that for repeating purpose, like, for the next phase and next phase, she's going to create this, she's going to create a new set of random looking labels. So she's not going to reuse the same random labels. Otherwise, by looking at this, multiple times by looking at these labels, the even will understand at least whether this was the previous inputs or it's a new input. So every time that Jeannie wants to send a new set of inputs, she creates a new set of random labels and create that. All right. So at this point, even now needs to do the evaluation part. So even becomes the evaluator, right? So what even has is a table which basically has 4 numbers. Even has no idea which one is for which output. It's just saying 4 random looking values, right? Strings. Another thing that even will see is just a random inputs that's supposed to be WGI, right? So it's either 0 or 1. Again, even has no idea whether this is 0 or 1. Okay. So now let's see what even should do. So remember that we have 4 different values. And what even needs to do is that adding his value, which is WEI, right? And he already has WGI. So if somehow even gets this WEI and use this one, he can basically decrypt these lines. And the one that he can decrypt is the one that these values correspond to. So for example, let's say G is equal to 0 and E equal to 1. Remember, we create an encryption mechanism that requires 2 keys, and based off those 2 keys, we can decrypt the system. So if those 2 keys are 0, 0, this line can be decrypted. If this input is 0, 1, this line can be encrypted is 1, 0, this line can be encrypted, and so on and so forth, right? So basically, if even has access to those 2 keys, he can decrypt the value that he wants. And the beauty of this is that these 2 keys only apply to one of these 4 lines, right? By knowing these 2 keys, even cannot decrypt the other lines. So for example, if the input is 0, 1, even can only decrypt this lines, and the key doesn't match with any other. So basically it creates garbage when trying to decrypt the others, right? So now the only things that remains is how even gets WEI. Remember, even has access to E, but has no idea what is the correct label for his input. So he doesn't know whether what WE1 and WE2 look like, right? So he needs to somehow get this, right? And the trick here is that, you might ask, okay, so why don't Genie just send these two labels to even? If Genie does that, then even can easily understand what's the inputs of Genie is. Why? Because essentially, instead of having two keys, now even has three keys, right? Even has GI, and also even has E0 and E1. So basically, even can decrypt two lines out of these four lines. And basically, by just comparing these two, even can understand what is the inputs of Genie. So sending both of these labels is not possible because that's break the system, right? So Genie only needs to send one of these two inputs to even, right? But then the question is, if even asks, so let's say even has input 0, if even just tell Genie that send me WE0, Genie obviously very quickly will understand that E is equal to 0, right? So even cannot just tell, give me label WE0, because that means implicitly that my input is equal to 0. And then on the other hand, even as I said before, cannot ask for both of the labels. So we need some sort of weird transfer, which we call oblivious transfer, that during this process, even ask for even gets only one label out of the two labels, but Genie does not understand which of these labels has been selected, right? So it's kind of like, even goes to the room and can only pick up one of the two balls that is inside, for example, a box or something, right? But again, even cannot take both, and Genie cannot know which one even has taken, right? So this is the key component in global circuits, which we call oblivious transfer, right? So now let's actually look at how the oblivious transfer or OT works. So just to give you a little bit more formal definition of what OT is. So OT is a protocol in which a sender transfers one of potentially many pieces of information. So in this case, we have a 1, 2. So we have two possible information, W0, WE0, and we have WE1. So one of these two labels, even wants one of these two. So sender in this case is Genie, right? So Genie wants to transfer either WE0 or WE1, but Genie has to remain oblivious as to which of these two she has been already transferred, right? So that's the key here, that Genie does not need to know which one she has sent, all right? And then on the other hand, only one of these two has to be sent. Genie should not send both of them to even, right? So let's see how actually OT will work. Change the color here. So let's actually go and see how the oblivious transfer works. So I'm gonna give you an example with Alice and Bob to make it more generic, all right? So I'm just talking about oblivious transfer at this moment. Just forget about W1 and W2 for a second. So let's say Alice has two messages, M1 and M2. In our example, basically, this becomes WE0, and this is basically WE1, right? So, but now for now, just a generic case, assume that, Alice has two messages, M1 and M2, and depending on what Bob wants, Bob needs one of these two. So let's say, for example, in this case, Bob wants M2, right? So just imagine, just without loss of generality, let's assume that Bob wants M2. All right. So here are the 4 steps that needs to be taken in order to create this this process. So let's go through them one more. The first thing Alice does is again creates two random values, x1 and x2, and send it to Bob. So just basically, again, think about this as two 8-bit values. Alice just randomly creates this and send both of them to Bob. Of course, at this point, no useful information has been communicated to Bob, only just two random values, right? Then what Bob does is create another random value k, and based on the message that he wants, he will send the encryption of k plus xb. So for example, so let's see what happens. So first of all, what Bob does is creating another random value and call that k, right? Then what Bob does is he's going to encrypt that k. So he's going to just do some encryption on k, and creates another random looking string, and then adds that encryption with xb, right? So xb here is either x1 or x2. So we are assuming that b is a binary value. So because Bob either wants M1 or M2. Remember, we are doing 1 to 2 oblivious transfer. If, for example, Bob wants to pick 1 out of 4, then B would be 0, 1, 2, or 3. But here, to make things simple, let's say there are 2 possible options and Bob wants to just pick 1 of them, right? So basically, if Bob wants M2, what he's going to do is that he's going to encrypt K and add X2 with it, all right? So this would be a new value called V. And Bob going to send V to Alice. And then again, if you look at what happens here, is that what Alice will see is the value V, right? But what Alice does not know what this value is, right? Whether it's whether B is equal to 0 or B equal to 1, because just a random looking value. The only thing Alice can do is basically doing 2 things, right? So Alice creates 2 candidate Ks, K1 and K2, right? How Alice is going to create that? Alice is going to subtract V with either x1 and x2, and then decrypt this value using the decryption mechanism that she knows. And this way she's going to get K1 and K2, right? But again, there is no way Alice knows which one is the correct value. She has access to x1 and x2. That's why she just subtract V with x1 and subtract V with x2, and then decrypt both of them and gets K1 and K2. Either one of these 2 is the actual value that Bob has been selected here. But at this point, Alice has no idea which one is which, right? So she just guessed that these are the two values, but in only 50% chance that this guess would be correct, right? And that's what we want. Then what Alice does is she's going to create this new variable called T1 and T2. And the way that T1 and T2 works is that she's going to add the message that she has with K1, and then add another message that she has with K2, and then sends these 2 values to Bob, all right? So what Bob gets at this point is getting T1 and T2. But the key thing here is Bob does not know cannot recover M1 and M2. Why? Because Bob has only access to the correct K, which in this case, for example, is K2, and does not know the exact value for K1. And the reason for that is Bob cannot decrypt this message here. And since he can only encrypt messages, but he cannot decrypt messages. Once we talk about public key encryption, we will show you how this is achievable. So what Bob only can do is encrypting messages, but Bob cannot decrypt messages. So what does that mean is Bob cannot know. So if Bob know what K2 is, which is in this case is equal to K, Bob cannot know what K1 is, right? So has no idea what K1 is, because in order to find K1, Bob has to be able to decrypt. And since we are relying on the security of the encryption mechanism, it is guaranteed that Bob can never know what K1 is, right? So what happens in this case is that Bob has access to T1 and T2, but since Bob only knows what K2 is, but does not know what K1 is, he's gonna do T2 minus K2, and that would be resulting in M2, all right? Because T2 is equal to M2 plus K2. So if we subtract T2 from K2, we'll get M2. And then if for T1, Bob cannot recover M1 because does not know what the value of K1 is, right? And that's the key here, that the reason that this method is secure is this, that at the end of this 4 steps, Bob successfully recovers M2, but does not know what M1 is. Why? Because Bob does not know what K1 does not know what M1 is, because Bob does not know what K1 is, right? So that's the key here. And on the other hand, if you look at the Alice point of view, you will see that basically what Alice sends at the end of the day is T1 and T2, but she does not have any idea whether T1 was decrypted or T2 was decrypted. So she does not really know whether message 1 has been used or message 2 has been used. The only thing that she knows is that it is guaranteed that Bob can only recover one of those 2 messages, and that's the security that Alice wants to have. So at the end of this process, Bob has access to M2, and Alice knows nothing about whether Bob has picked M1 or M2. On the other hand, Bob also has no way of recovering both of the messages, and Bob can only recover one of these 2 messages, right? So that's the fairly complicated oblivious transfer algorithm, which out of these 4 steps, both of these 2 can basically do what they want. So remember, going back, what the oblivious transfer wants to do is that a sender transfer one of the potentially many pieces of information to a receiver, but remains oblivious as to which piece of information has been transferred, right? And then this way we have shown. Alice has 2 pieces of information, M1 and M2, but does not know whether Bob has selected M1 and M2 or M2, right? So going back to our GC, we are at this stage where Even is the evaluator. Even has access to 4 values, which are the encrypted values of the truth table. And also Even has access to GI, right? Has access to the inputs of Gini. What Even does not have is the label for his own values, because the labels, remember, the labels were created by Gini, so Even does not know which label is which, right? So he needs to get either, if his input is equal to 0, he needs to get WE0. If his input is equal to 1, he needs to get E1, right? How do we do that? We already now know that how do we do that? We use EOT. So this basically becomes M1. This becomes M2. We do OT, and after this process, Even either gets WE0 or WE1, right? So that's the process that we do. And now what Even has is WGI and WEI. So I is basically depends on what the inputs they have. And also he has access to 4 labels, right? So now what Even can do is basically he can try his key and decrypt all of these 4s, right? He gets these 4 values. Let's call it T1, T2, T3, T4. And remember, since this key only can be applied successfully to one of these four values are actually a valid value, and the other three would be some sort of a garbage, which means that, so remember, Alice also has these four values here. Let's call it T1 prime, T2 prime, T3 prime, and T4 prime. What happens here is that when we are sending this, we are sending T1, T2, T3, and T4. Only one of these four match with these values. The other three is just garbage values, which is not matched, right? The one that matches is the actual ones that these two keys correspond to, right? So even will decrypt all four, send all four, but only one will match. And since Alice knows which one is matched, so Alice basically gonna compare these two values here and here, here and here, here, and only out of these four, only one of them will be matched. Let's say, for example, in this case, this one will match. So then what Alice would do is just tell which one is the match. In this case, this one, and then just announce the results, and that would be the outcome of the gate, and that's what both of them wants. Just remember that Alice also did a permutation. So basically, this does not mean this is for 0, 0, this is for 0, 1, and so on. Remember, we just shuffle this around, but remember, Alice knows how the shuffling works as well. So although this T3 match with T prime tree, she also knows that, for example, T prime tree is actually assigned to 0, 0. So in that case, what happens is she will announce that the output is 0, 0, which in the truth table, 0, 0 is equal to 0. So what he's going to do is that he's going to say that the output of this gate is 0. All right. So that's at the end of the day what Alice will report. Right? Again, we are assuming that everybody following the protocol correctly, so it's not that Alice will announce incorrect results or something. Both of them wants to evaluate this function correctly, so that's why Alice will present the correct results. There are ways to making sure that this is actually the case. We're not going to talk about it, but just know that this is the way that this works. All right. So I guess I'll cover enough about this. So let's actually move forward. If there are questions about this, please use Campus Wire to ask questions, and I'll happy to answer. Probably other people can help you with answering the questions. All right. So this is just the garbling circuits. Obviously, there are many challenges with GC. The challenges that usually happens is that there require a lot of communication between the two parties. So for each round of evaluation, one of the users, in this case Ginny, had to send 4 labels to the output to the evaluator, which was even. And not only that, even also needs to do 1 round of oblivious transfer with Ginny. Then even needs to send back the results to Ginny, and then Ginny can actually announce the results. So there are multiple rounds of communications between the two parties. And if the communication itself is a bottleneck, that could be a huge challenge, right? So for example, in the context of machine learning, just imagine that for every multiplication that we need to do a round of communication between the two parties, and that could be a big challenge. And because of that, there are lots of optimization. Another challenge is, so basically what we do, again here, for every 2 1-bits inputs, right, we are creating labels, and we are basically doing rounds of encryption and addition and so on and so forth for just evaluating 1 gate, right? So very similar to fully homomorphic and homomorphic encryption in general, the performance is one of the key challenges. Why? Because essentially for just, for example, adding two 1 bits, so A and B, we kind of need to add and multiply and subtract much more bigger inputs. So for example, if the labels are 8 bits, we are basically saying that each AND of 1 bit now results in 8-bit values that needs to be multiplied and added and so on, because we do encryption and decryption and all those things in just one round of evaluating ANDs. So the computation bottleneck is huge compared to normal computation, unfortunately. And on top of that, there is a communication bottleneck going on as well. So that's another added challenge. So communication and performance are the two challenges in garbled circuits. Of course, there are lots of optimization in this domain. There are ways for reducing the amount of evaluations. There are things like 3 XOR or AND half AND gates and all those things, which because of time, I'm not going to talk about, but probably if you just, read a little bit about GCs, you'll learn about those things. There is another trick that usually been used, and this is use of what's called an offline phase versus an online phase. So what during the offline phase can be done is that, remember, for example, that Genie needs to send all the labels and tables to even. What Genie can do is that basically create list of labels for all the gates in the systems and send that beforehand, even before the evaluation begins, because essentially these are decorrelated from the previous gates, right? So all Genie needs to do is creating like 4 random labels for each of the gates that exist in the network, and then she can do it in the offline phase only one time and send it over to even, right? And so in this case, then all this process of sending and receiving the tables and so on can be eliminated during the online phase. The only thing that during the online phase needs to be done is basically sending the inputs of Genie and receiving the value that it has been evaluated by even, right? So the number of communication and the quantity of the communication is much, much less, right? So we can significantly reduce the overhead of the communication this way. And then to reduce the computation overhead, there are lots of things that happens for the evaluation. So for example, we may not need to send all the 4 labels. People have shown that sending only 3 labels would be enough, so on and so forth. So there are methods in order to reduce that computational overhead as well, which again, we're not going to talk about, but if you're interested, go and take a look. Of course, one question that you might have is that if you want to compare GC with homomorphic encryption, what are the differences? So the big difference is that GC requires some communication, right? Whereas homomorphic encryption does not need communication, right? Homomorphic encryption, the only thing that homomorphic encryption needs is just one round of encrypting data and sending encryption to the cloud, right? So in this case, in terms of communication, of course, homomorphic encryption is much, much better than garbled circuits. On the other hand, computation of garbled circuits is much more efficient. So GC is much more efficient than homomorphic encryption. The reason for that is because of these optimizations. So the one round of just evaluating an AND gate and so on is quite fast, especially if we use the technique of offline phase. So we actually do the offline phase first, and then during the online phase, the only thing that needs to be done is going through those 4 values, doing one oblivious transfer, sending back the results, and that's it. All right, so that process could be much more faster than homomorphic encryption, such as doing things like bootstrapping and so on and so forth. So that's another thing. The other thing is GC is not somewhat, so there's no notion of noise in GC. So we don't have to be worried about the depth of the network and so on and so forth. Whereas for homomorphic encryption, we either have to do fully homomorphic encryption and solve that issue, or we need to use somewhat homomorphic, and in that case, we need to know the depth of the network and so on. So there's no notion of noise in GC, which is a good thing, especially for complicated networks. Another good thing about GC is that GC works with nonlinear functions as well. So remember that for homomorphic encryption, we said that we only can evaluate it using polynomials. But for GC, the only requirement is that if we can show it using gates, we can evaluate it. And you know already that, for example, in gates, we have things like comparators and things like that, which essentially do the things like, less than or equal or greater than and so on. Right? So we can technically, implement if conditions in some sense in Garble circuits. So that's the challenge. So just to kind of, to summarize, the biggest downside of Garble circuits is this huge communications that require, right? And since most of the kind of communications becomes the bottleneck, Garble circuits may not be a great option in some cases. And that's where homomorphic encryption gets an edge, right? But in most of the other departments, Garble circuits is usually better. But of course, both of these are ongoing and open-ended solutions and problems. So there are lots of research in order to optimize both of them. So for example, there are lots of work these days on how to parallelize homomorphic encryption, right? And if we can do that, then this terminology here may not be no longer valid. So we can have very fast homomorphic encryption mechanisms, then which kind of like make these two almost similar. And if that becomes the case, then because of the fact that homomorphic encryption does not have this overhead of communications, then in that case, the overall end-to-end, latency of homomorphic encryption might be less than Garble circuits. So there's no answer that which one is the better than the other. Really depends on the setup and the problem that we're trying to solve. But it could be in some cases one has a better performance than the other. All right. So now let's just very quickly go over the other methods that exist in, let's see how we're doing with time. So, okay. All right, let's continue. So let me just very quickly go through other methods in privacy preserving. Another popular method is what's called a secret sharing. So the secret sharing is basically saying that, if we have the secret value, what we can do is that we can divide it into the pieces and then just share these pieces with different users, right? So if let's say we have 3 different players, we can divide this secret into shares and then share the shares between users. In this case, there are methods that guaranteeing that, if the user, of course, don't collude with each other, they cannot find the final value, right? So for example, let's say our secret is 18. What we can do is that we kind of like make it into like, addition of 3 different numbers and then share this with different users without knowing all the pieces. We cannot know what the final values is, right? There are methods for knowing how to do it securely. It's not just, every secret sharing is actually secure. You have to be very, very careful of the ways that we do the secret sharings. There are methods for doing that. So if you're interested, go in and check it. For all of these secure secret sharings, there's again some notion of which one is how much is the majority and how secure the system is. Some of them are, let's say, secure if the number of malicious users is smaller than half of the players. There are some other cases that if it's less than n-1, the system will work. There's like more relaxed versions as well, and so on and so forth. So the notion of majority is important in secret sharing, and it could depend on one scenario from another scenario. So this is just for storing the value. So that's the original secret sharing is just for storing specific value. We can just divide the shares between users. But people have shown that you can actually do operations on secret sharings. So similar to the way that we showed that, for example, homomorphic encryption can be evaluated using addition and multiplication, people have shown that, if you have secrets such as S1 and S2, so basically we have a secret that is shared between S1 and S2. If we share it in some way, we can actually show that, for example, we can add this with some other values. And then at the end of the day, if we gather these two secrets again, we can recover what S was or what F of S was, right? So the same way that homomorphic encryption works, right? So if we can, on the partial secrets, we can do addition and multiplications, and then finally recover the secret, and the secret would be the function that we wanted to evaluate, then we basically get the notion of homomorphism on secret sharing as well. So that's another idea that secret sharing has. Secret sharing, unlike the other methods, usually requires some sort of like what's called a dealer or some sort of centralized intermediator. Mostly in case of like multiple parties, one of them can assume this role. So it doesn't have to be like a centralized server. It could be one of the players in the game, but there has to be some sort of dealer that, gather and scatter this values and so on. Right? So secret sharing is another example. It's usually much more limited than homomorphic encryption and multi-party computation. That's why it's less popular in some cases. But what happens is that, secret sharing is actually usually combined with homomorphic encryption or multi-party computations, because there are some scenarios where secret sharing can be much more effective and impose less overhead. And in those scenarios, secret sharing could be a very, very good candidate, right? So typically what you will see in the literature is that people combine secret sharing with one of these two methods in order to optimize the performance, right? Another option is what's called differential privacy. So differential privacy is slightly different than what we discussed so far. Essentially, this differential privacy tries to answer this fundamental question that instead of when, let's say, we want to share a data set with the open world or for a specific user, can we share this data set in a manner of which that the information of individual records cannot be known? So let's say I have a data set D, which has different public records. Of course, if I publish this by just going through this records, everybody can understand what these values are. You can anonymize these and so on to remove some of these informations. But the idea of the differential privacy is basically saying that, assuming that we want to do some aggregate to evaluate some aggregate behavior of the data set. So remember, we're not looking at individual records, but we are looking at the aggregate behavior of this data set. So for example, we want to measure the mean of this data set, or the variance, or it could be any other like statistical behavior of a data set. So let's say we want to measure these. So instead of like actually publishing the raw data set and say, okay, go and calculate the mean or the variance and so on, what we do is basically adding some sort of what's called noise to this data set and publish this noisy behavior. And the interesting thing about the differential privacy is that there are methods to guarantee this, that if we do that and apply the same algorithm to two data sets, the original data sets and the data sets that created by differential privacy, and the algorithm could be, again, the average or some sort of statistical methods, the values would be almost the same with some thresholds. So basically, there will be some thresholds that is predefined, and this threshold basically saying that these two aggregate behavior will be as close as this amount of threshold. So let's say 2 to the power of, I don't know, minus 32. So it's like this close, these two data sets will be to each other. But on the other hand, knowing the difference between individual records cannot be known by some probability, which is usually defined by this epsilon, which in this case is basically what it's saying is that if I have two data sets and they are only different by just one record, right? So for example, if I change this record to another record, or if I just remove this record and create D prime, the chances that if I publish D prime, the adversary can understand what the original value in the D is usually less than this P epsilon. All right, so this is usually what the differential privacy will give us. Just to give you intuition, the idea is we want to publish the data set and we want to do some statistical behavior on this data set. Instead of publishing the raw data set, what we're going to do is that add noise in some sense, which we use differential privacy algorithm for doing that, and publish this noisy data set. And then if the user wants to do the aggregation on this noisy data set, we will guarantee that the values that he's going to get would be as similar to the original data sets plus some delta. So the added noise to the system would be only as small as delta. And if this delta is small enough, basically this approximation is good enough and we will have it, right? On the other hand, the guarantee in terms of the privacy that differential privacy will give us is that we're saying that basically if you choose this for this specific data set, the chance that you can actually recover an individual user would be smaller than some epsilon. And in this case, it's usually epsilon is very, very small, right? So what happens is basically we get kind of best of both worlds in some sense, where we get almost similar accuracy in terms of the aggregation behavior, but we get very, very small chance of actually recovering individual records into the data set, right? So that would be an ideal scenario where we are looking at. Of course, there are multiple noise addition strategies. There are lots of discussions about the guarantees that differential privacy would give us and so on and so forth. The biggest challenge with differential privacy is the notion of utility versus privacy, because essentially we are dealing with two things, right? The delta and epsilon. And unfortunately, if we want to increase epsilon, so we want to decrease the chance that actually a specific record being recovered, the delta has to increase. And if the delta increases, it means that the accuracy of our aggregation will decrease. So basically, the utility, which in this case, the accuracy of the aggregation, the statistical value that we're looking for, will decrease. But on the other hand, the privacy will increase, right? And then if you want to increase the accuracy, then the privacy will decrease. So there's this trade-off between, utility and privacy that needs to be dealt with in differential privacy. So that's the biggest challenge. Again, differential privacy is also an ongoing research, and people are trying to see what are the best way of fixing this, right? So this is the, just to recap, this is the problem that the differential privacy tries to address. It adds noise to the aggregate behavior using some specific, distribution that we didn't talk about, but if you're interested, you probably can go and take a look. And this way we get some sort of notion of guarantees about differential privacy. And so what is the application in machine learning? Usually what happens is for differential privacy, the biggest use case would be something like, training data, where essentially instead of like publishing the specific records, we can add some noise and publish the training data set using that. And there are methods that shows that how much information is being leaked and so on, but still we can achieve certain level of accuracy for the machine learning. All right, so that's usually the case for differential privacy in machine learning. I think one of the papers this week, somebody gonna talk about this, so you'll learn more about it. I think you already read the paper as well, so we probably have some ideas of how differential privacy can apply to trustworthy AI and machine learning. All right, so the final thing that I want to discuss is the notion of what's called decentralized machine learning, where the idea is basically let's distribute data between nodes instead of like everybody sends data to the server and the server do that, for example, the training. Let's actually do this in a decentralized model. It's usually as like people have different, values. This is usually during the training. This is being used. So decentralized machine learning is mainly applied to the training. For the inference, then it's more of like, the methods that I described, such as multi-party computation and so on. It could be also applied to something like, blockchain, which we're not going to talk about in this lecture, but maybe later on in this course, if you have time, we'll talk a little bit about blockchains as well, where you want to evaluate the function in this decentralized manner. But here we are mainly talking about like assuming that different people have individual records, and we want to train a model based of these distributed values. What we can do to achieve that, there are the most popular solution for this is what's called federative learning, which is actually being used by large companies such as Apple and Google these days. There's also minor different solutions such as split learning and instance learning and so on and so forth. In all of these scenarios, sorry about that. Give me a second. All right, so I think we are back. Sorry for the glitch. So yeah, so the idea of decentralized learning is this. We're going to have papers about, I think, federated learning, so we will learn a little bit about this. So the idea is basically, in most cases, the idea is that, there are different users with different, input records, and there is this centralized model that sits into the cloud, right? So there's this cloud, there's this machine learning model, and what we want to do is that we're going to use this data here in order to train this model, right? So what we can do is basically this trick that, the model here can be sent to these users. These users can locally run the training algorithm and then partially update the model. So they're gonna send the partial gradients back to the cloud. The cloud will update this model based off these gradients, then move to the second one, to the next one, and next one. So basically what would be available to the open public would be this partial gradients, and there are no known methods for example, reverse engineering these gradients in order to find the actual, raw data. But on the other hand, by just combining these gradients, people have shown that the machine learning, the model that will be created by this partial gradients would be almost as accurate as the model that would be trained, in a centralized manner, right? So if we can achieve this, like kind of like getting it reasonable accuracy, then what happens is that then the server never see the actual raw records here, right? The only thing that the server will see is this partial gradient here, which does not have enough information to recover the individual records, right? So that's the main idea of decentralized methods specifically for federated learning. There are others such as instance learning and split learning, which we don't have time to talk about. But if you're interested, definitely go and check it out. So there are multiple challenges in decentralized learning. The biggest challenge is that, unfortunately, these methods are not relying on hard problems that's typically used in cryptography. So when we were talking about multi-party computation and homomorphic encryption and secret sharing and even differential privacy, all of that has provable guarantees, right? which means that there are some hard problems that it's provable that cannot be solved, at least with the current status of things. And these things are relying on those hard problems. So it is guaranteed that adversary cannot find information. For these decentralized machine learning, such as federated learning, split learning, and so on, unfortunately, there is no notion of these guarantees, these provable guarantees. So it's more of like based on heuristics and based off some empirical study that people cannot find results for it, right? So that's the key challenge in decentralized machine learning that does not use provable methods such as DPSS, HE, or MP. All right, and so that's the key challenge, and so that's number one. And the other problem is that since this is like done in decentralized manner, the biggest issue that we are facing is that they are very susceptible to adversarial attacks, including data poisoning and membership. Remember when we said about data poisoning, we said that you have to download the data set that somebody put some poisonous records into there. Since this decentralized machine learning is naturally actually reading inputs from different users, maybe one user can just very simply just send out poisonous data. So the opportunity for conducting poisoning attacks in federated learning is much more higher than normal systems that are centralized, because essentially their input records is coming from multiple different instances. But there are lots of ongoing research on both attacks and defenses in these scenarios. So the attacks obviously trying to make it more effective, make it smaller and get the footprint smaller and so on. On the defense side, what is happening right now is basically this idea of how to make sure that, for example, if only X percentage of samples are poisonous, our system is still secure. So it's kind of like trying to deal with this notion of what would happen even if a certain percentage of the inputs are poisonous. And then there are systems methods in order to verify and authenticate users and inputs and so on, anomaly detection. So there's actually this idea of attacks and defenses for decentralized machine learning is really active area of research. Right, and the same can happen for membership inference and privacy attacks as well. People have shown that, for example, by just sharing the gradients, it's not guaranteed that we are hiding the entire information. There could be still sensitive features that we are sharing no matter what. So that's also another research, and the reason for that is usually because of the lack of this provable guarantee. So we really don't know exactly what is the upper bound of information that can be leaked. And the other options, so there is like a very like current and new method. So basically, this motivation that we have that okay, so this motivation that we have that essentially these provable guarantees, provable methods such as MPC and HE and so on can give us this guarantees, but on the other hand, they suffer this huge performance issues, right? So the performance is terrible, but of course the security is great. So in order to make these useful in real cases, we kind of need to find a common ground, a nice trade-off between these two, that maybe we can leak some information, or in some cases it's secure to do it and so on. But on the other hand, achieving significantly better performance. So kind of like the solution, the ideal solution sits somewhere in between these. A good compromise of these two might be a good solutions. And that's the major motivation for these kind of like non-cryptographic ad hoc methods. So basically, lots of works these days are focused on notion of encoding. So the idea is that we have a record, an individual sample, it's an image. What we can do is that instead of sending this information, we can map it into another domain with different features, and then send this information to the cloud. And what happens is that during this encoding process here, if we can maybe like, remove or mask some of the sensitive features in this original image, then this record that we are sending, this encoded record that we are sending, does not have that information, and then we can send that safely to the cloud. The beauty of this is that once we send this to the cloud, then the cloud can just do the computation normally, because it's just a normal record as any other things. The overhead would be just this additional encoding method here, but this could be proven that it's not significant and can be done pretty efficiently, right? So instead of actually dealing with like homomorphic encryption and then starting all the way, like all the multiplication additions has to be done using homomorphic encryption in the cloud, something like encoding can kind of fix this problem. So we have just one short, round of removing information, and from now on, then we can send information to the cloud, right? So that would be the idea of combination of homomorphic, a substitution of homomorphic encryption with things like encoding or ad hoc encryption. All right. So this is like, if you're interested, take a look at things like, for example, insta-hide or adversarial feature learning to learn more about this. The advantages, as I said, is the performance. The disadvantage is that similar to, for example, federated learning, there is no provable guarantee. So we're not really sure that, for example, is the information really removed, or if the adversary can use a better, for example, algorithm, they can recover this information and so on. So that's the challenge that we are facing today. All right, so I guess that's the end of the presentation. So what we discussed so far was, so we started with like adversarial machine learning, right? We talked about poisoning and invasion and so on. We talked about defenses. Then we moved to privacy attacks, right? And we said that things like, membership inference attacks and model extraction attacks and so on. Then we moved to privacy preserving computation. And we essentially said that if we want to evaluate a function on an input, and we don't want to send this input to the cloud, what are the possible scenarios? And we talked about homomorphic encryption. We talked about multi-party computation. We talked about secret sharing. Talked about differential privacy. And then we also talked about like these ad hoc methods such as federated learning and ARL and ad hoc methods and so on and so forth, right? The issue with all of these is kind of the notion of performance, right? They are secure, but the performance is the major challenge. And that's why we kind of like, shifted toward this method here, which give us the performance that we want, but unfortunately still the privacy guarantees that comes with them is yet to be known. So we need lots of theoretical work in this domain in order to actually find this information. So, so this is the current state of the research. So people are trying to improve the performance in these systems using different techniques such as hardware techniques, system techniques, and algorithm techniques. So that's one area of research. The second area of research is actually coming up with this compromise between the privacy and performance and achieving both at the same time. That's where kind of like hybrid methods, which is basically combination of some of these. So people have proposed combining homomorphic encryption and multi-party computation, combining homomorphic encryption with secret sharing, and so on and so forth, combining differential privacy with federated learning, and so on. So these are the methods that have been proposed, which kind of like, can create a right balance between these two. So that's another area of research. So yeah, that's it. What we're gonna show and talk about after this point is that what we can do in hardware to provide some security. So one very interesting thing to show is that we actually can provide privacy preserving computation in hardware. We're going to talk about it using this notion called trusted execution environments, or TEs. So sometime next week, we're going to talk about those things, but we're also going to talk about other issues with the hardware and how to fix those issues. So starting this week, we're going to talk about those interesting things as well. All right. So if you have any questions about this specific lecture, think it's getting a little bit long, but I mean, I wanted to just make sure that we cover all the important things because this is like an active area of research. So it would be nice to actually knowing more about these things. So if you have question about this, definitely put your question in Campus Wire, and hopefully either me or some other students can answer your questions. All right. So thank you so much, and see you on Wednesday.